the process concept, and it was generally to do with the processes, and so we saw the concept, process scheduling, the operations on the processes. Then we looked at the interprocess communication, IPC, and how it's done in different systems, the memory systems, and then the shared memory systems and message passing systems. So we did say that a process concept, generally we have a process which is generally a program in execution. And so an operating system executes a variety of programs that run as processes. And then we also talked about the multiple parts in a process image, which include the program code, the current processor state, and then we looked at the stack contents, which typically contain temporary data or data. And then we looked at the data section under the multiple parts in a process image, which contains global variables, and then the heap that contains memory, which is dynamically allocated during the runtime, and the other resources under the process image, which include the open files, command line arguments, environmental values, and others. We also went ahead to say that a program is a passive entity that is stored on the disk, and that program is normally an executable file. Take for instance a word processor or a spreadsheet or maybe PowerPoint, a presentation, processor, rather presentation program, and then the process is what is active. So you could have a couple of files stored on your machine, some of them open actually, but if you're working on a particular document, then that's the process, because it becomes active now. Meanwhile, the program is running in the background. It's passive, but it helps you work on a particular document. It could be your presentation, it could be your report, or maybe you're trying to settle your finances. And then we also looked at the different states of a process. And remember, we had the new, when the process has just been created, then the ready, when the process is ready to run but is waiting to be assigned a processor, then running, where we have instructions that are being executed, and then waiting, and this is sometimes the process is waiting for an input or output or one event basically to occur so that it can continue, and then finally we had the termination state where the execution is complete. Then we also talked about the process control block, which is generally information associated with each processor, and it of course has the process state. It has the program counter, which tells the location of the next instruction to execute. Then it also has details of the CPU registers. It has something to do with the CPU scheduling information, the memory management information, accounting information, and then the input-output status. Then for the scheduling, we saw 3 levels of scheduling, and that was long-term scheduling, where the decision is about which processes are admitted into the system, and usually this is just in batch systems. Then there is medium-term scheduling, where the decision is about which processes are memory resident, and the short-term, which is about which memory resident process gets the CPU next. And we then went on to the process scheduler, and we did say that the objective of this process scheduler is to maximize CPU utilization, and it quickly switches processes onto the CPU core, and it maintains the scheduling sequences of the different processes, changing between ready, wait, and so on. And then we got to this CPU switch from process to process, and that we actually refer to as context switch. And we said that when a CPU switches to another process, the system must save the state of the old process and then load the saved state for the new process via a context switch. And we saw a diagram of how that happens. Generally, try to put it in the diagram, but that's how the operating system works. And we did say also that the context switch time is overhead, and therefore the system does no useful work while switching. And this context switching also is time dependent on hardware support, and therefore we have multiple contexts that could be loaded at once. Then we did talk about also operations on the processes, and we said there were two. There's the process creation and process termination. And for the process creation, we said that the parent process creates child processes, which in turn create other processes, forming a tree of processes. And there were two scenarios where you could, rather various options in which the different processes could run, especially under process creation. And there is the execution option and then the resource sharing options. So under the resource sharing options, we did say that the parent and children or child can actually share all resources. And then there's a scenario in the resource sharing where the children share a subset of the parents' resources, and then a scenario where each of them actually has their own resources. In other words, they do not share resources. And then for the execution, normally, rather, we could have two cases as well: the parent and child executing concurrently, or the parent waiting for the child to terminate, and then it also terminates. And then for the process termination, we said the process executes the last statement and then asks the operating system to delete it using the exit system call. And we also looked at scenarios in which the parent may terminate, and these were sometimes the child has exceeded the allowed resources, the allocated resources, or allowed resources, and then the task assigned to the child is no longer required, and then sometimes the parent is exiting, and of course the operating system realizes that, okay, the parent has exited and therefore the child is left as an orphan, and therefore it just goes on to also terminate it. And then we also talked about cooperating processes, and we said that we could have two processes which can either be independent or cooperating with respect to each other. And when they are cooperating, then it's for purposes of sharing information, or to speed up a computation, or to increase modularity of an application. And of course, that's all aimed at improving the efficiency. Then we finally talked about the inter-process communication. And this was really also under the cooperating processes, where we said that they need the inter-process communication mechanism, which allows them to share or exchange data. And there are two models for the inter-process communication, and we talked about the shared memory, and the other was message passing. So for the shared memory, we say there's an area of memory that is shared among the processes that wish to communicate. And so with threads, the sharing memory is actually easy. And today we shall look at threads and concurrency. And then the communication is under control of the user's processes. Then when it comes to the IPC with message passing, we said this was a mechanism for processes to communicate and to synchronize their actions. And we also saw that the inter-process communication provides two operations, and that is the send and receive. And for the send, it has two fields, the destination address and then the message it's sending, and then for the receive it has the source field, source of where the information is coming from, and then the message that has to be received. Yeah, then we finally looked at direct and indirect communication, where we also did say that processes must name each other explicitly. And so you have the sender and the receiver, and then for indirect, you have still the sender and the receiver, but the communication actually happens through a mailbox as opposed to the direct communication. So, in a nutshell, that is what we did yesterday, and so today I would like us to continue and look at threads and concurrency, and then we shall call it a lecture and a week as well. So for those of you who came in late, I did say that today I'll most likely use an hour, and we're going to cover threads and concurrency. So under this, we're going to look at an overview of threads and concurrency, then we'll look at the multicore programming, then look at multi-threading models, then we shall also look at thread libraries or talk about thread libraries, then implicit threading, then we'll look at threading issues, and then just end with an example of operating system example of threads under Linux. So an overview of this is one thing that is happening currently is that modern systems actually are multi-threaded, and when we talk about a thread, we are generally talking about the smallest sequence of programmed instructions that can be managed independently by a scheduler. And then it could be a single sequential flow of control within a program. So just like we said yesterday, we have a program which is passive, and that's the bigger thing, Microsoft Word, for instance, and then we have the processes. If I open different files that I'm working on, those are the different processes that are running within that program, Microsoft Word. So that is, but it could also generally be a word processor, okay? So you could open up also a Notepad. Notepad is a processor that runs into in a program which is just a word processor. So basically a thread will be the smallest sequence of a programmed instruction. So part of that, if maybe you're doing a save operation, if you're doing a delete operation, if you're maybe enabling, rather, if you're aligning center or right, that's a small sequence of a programmed instruction, because you see, it's an instruction. So if you want to align, yes, it's a programmed instruction that you're actually carrying out, but it's managed independently by a scheduler. So threads run within applications, just like I've been saying, and we have multiple tasks with the application that could be implemented by separate threads. And so we could have the update display, and then you could also have the fetch data, maybe from memory, that's for the OS, and then you have spell check as well, and then answer a network request. That is, if you have, say, client-server kind of arrangement. And so we also have the process creation, which we talked about yesterday, and in this case it's heavyweight, while thread creation is lightweight. So process creation is a bigger aspect. Just like we'll see, a thread actually can run within a process, okay? So that's why we're saying process creation is heavyweight and thread creation is lightweight. And so you could have simply code, or you can simplify the code and then increase the efficiency. That is why the threading is now being taken on by many modern applications. And of course, many of the kernels, operating system kernels, are also generally multi-threaded. Then, having seen the overview, we then have single and multi-threaded processes. And when you look at that diagram over there, for the single-threaded process, it has a single thread running as the entire process or within the process. Then for the multi-threaded process, we have one process running, but with multiple threads running. And when you look at these two, for the multi-threaded process, it actually has more like the same arrangement as the single-threaded, but in multiple form, if I will. So you still have the program counter, you have the stack, you have the registers, and then of course you have that layer of the code, the data, and the files. So you realize that of course the multi-threaded processor will be faster compared to this. So this more or less runs one process at a time because it has a single thread. And so when we talk about processes and threads, and when we talk about a thread as a lightweight process, it's just a unit of dispatching. So the thread is a unit of dispatching, and then the process or task is a unit of resource ownership. So basically, in this case, the thread more or less runs within the process and will not have more power or more privileges over the process. So in other words, if the process kind of gets terminated, then the thread also will cease to run. So process threads are just to help improve the efficiency, simplify the code, and make, of course, the entire process more efficient. And multi-threading here is the ability of the operating system to support multiple concurrent paths of execution within a single process. So remember, we said that threads run within a process. So you could have multiple threads within a single process, and we also say the thread is just a single instruction or a small bit of programmed instructions that could be running in an entire process. So multi-threading is just the ability of the operating system to support the multiple and concurrent paths of execution within a single process, and that is aimed at achieving efficiency in delivering the different tasks that are running on the computer. And then when we talk about the single-threaded approaches, we're talking about a single thread of execution per process, just like we saw in the other diagram. And the concept here is the concept of a thread is actually not recognized because more or less the single thread is the process. So it's really referred to as a single thread approach, but more or less a single process. And the example of that is the Microsoft DOS disk operating system, where you have, the command line and you're able to run your things there. And I think it makes sense because you can open a couple of things on the command drive, but you cannot open them concurrently, okay? So you have to run one at a time, as opposed to if you have a GUI where you can open so many things and work on them at the same time. And then for the multi-threaded approaches, it's one process that can have multiple threads, and multiple processes can have multiple threads per process. So we have a process with multiple threads, and then still we could have more than one process having still multiple threads per process. And this happens in a Java runtime environment. That's one of the examples, and many others, but generally in like a programming environment. And then talking about the multi-threaded service architecture, we generally have our client. Say if you're looking at a client-server architecture, we have the client, we have the server. So the client will send a request to the server, and so the server will then generate a thread or create a thread to service the request from the client. And so that thread will be worked on. But remember, this is a client-server approach. So there's one server that's actually being, that's servicing so many. I'll take, for instance, an example of workstations, maybe in a lab. Some of you have been to Lab 4, that thin client lab. You all fetch resources from a central place. So many students are there, for example, and they desire services from the same server. So it creates a thread to service a request from one client, and as the server listens in for additional client requests. So as the requests come, it creates another thread that is serviced. So you realize that it's the same process of request, but you generate different threads within those requests, and everyone is actually serviced, assuming you don't get many calls that exceed the resources available. So what are the benefits? The benefits of multi-threading is generally to allow continued execution if part of the process is blocked, especially, and this is important for user interfaces. So you may find that maybe for some reason, maybe one of the clients needs maybe to log in and they've not yet logged in. So that process is kind of blocked until you actually log in to get access. And then, of course, what happens is other threads will be continue to be serviced. And then for the resource sharing, there's another benefit is resource sharing, where you have threads sharing resources of a process, and this is easier. It is easier than the shared memory or message passing that we saw or looked at yesterday. And then it is cheaper than the process creation, and we also have the thread switching being lower overhead as opposed to the context switching that we looked at yesterday. And then there's a possibility of scaling it up in that the process can take advantage of multi-core architectures. So those are some of the benefits of multi-threading. So yes, I was looking at a bit of the chat, and someone was talking about bad gateway. Yes, actually, when you get that response, especially on Mwele bad gateway, it's really resources are actually more like all used up. Okay, so there are many calls that have been sent to Mwele and it has run out of resources. It can't handle any more requests, and so you get that bad gateway. Yeah, so of course, yeah, there was work around it, you know. They said it had gotten better, especially during exams, but I think, okay, the good thing is that exams, there was a single exam each day, and I think that limited the number of people trying to send requests to it. But I think after the exams, lessons have begun, so it's the entire university, so to speak, everyone accessing it, even lecturers to put notes to do what. So yeah, from time to time, especially if, for instance, people are working or checking Mwele maybe between 10 and midday, yeah, you might get some of those things, or even at night. But at night, it's much faster and better because many people are, you know, relaxing, and so you won't get that signal. But yeah, thank you for dropping that in the chat. Next, we'll look at the multi-core programming. And remember the other day, someone asked the difference between multi-core and multiprocessor. So multi-core is a scenario, or is generally just having a single processor with multiple execution units. And if you look at some of the computers you have now, it is a single core, rather one computer, a processor. They say it has dual core or 4 cores or 3 or something like that. So multi-core is a single CPU with multiple execution units, and then a multiprocessor is just a system that has two or more processors. Then we have, when we talk about multi-core programming, we are talking about systems generally are putting pressure on programmers. Multi-core or multiprocessor systems are putting pressure on programmers, and they bring challenges that include dividing activities. So as you do your code, how do you write your code? You need to, how do you divide it well, and how do you have a balance? Then when it comes to data splitting, how do I get my code run faster by getting it to, split? We're going to look at parallelism and also task and data parallelism, and we see how the different ways in which the operating system will deal with this. And then there is also the issue of data dependence, and then testing and debugging. So those are some of the challenges that come for the programmers, and of course how they need to write their code well to run with the existing processors. And so we have parallelism, which implies a system that can perform more than one task simultaneously. And then we have the concurrency, which supports more than one task making progress. So parallelism implies performing more than one task simultaneously, and then concurrency supporting more than one task making progress. So for concurrency, you actually have a single processor or a single core, and you have a scheduler that will provide the concurrency. And then we go on to look at, if we bring it in a diagram, at least then it kind of makes more sense to try and visualize what happens in the OS. So we have concurrency versus parallelism, and for the concurrent execution on a single core system, remember a core is just an execution unit, okay? So we have this single execution unit with like 4 tasks happening. So the concurrency will go like, for the first task will be done, then the second, the third, and the fourth. And like we've been mentioning previously in the previous lectures about time slicing and everything, each task could have a different time, or should be, it could be, has to be processed or run maybe for 5 nanoseconds, and then task 2 also will be run for 5 nanoseconds, and so on. So you kind of the scheduler will deal with each task for a specific period of time until it gets to the end, and then it will resume again until it gets to the 4th task, and continues like that until the entire tasks are actually executed. But remember, as one gets executed and gets terminated, we get a new one. We get a new one, of course, until such a time when there is nothing and it's just idle. Then for parallelism on a multi-core, for instance, here we have 2 cores, okay, 2 execution units. It could be one processor with 2 cores, so 2 execution units. It can divide the different tasks in the different cores. So if you're able to see the diagram, we have task 1 and task 3 running on core 1, and then task 2 and task 4 running on core 2. So of course, if we are to compare these two, then it's most likely that this particular system will actually deliver the output faster than this other one. But of course, all those are different ways in which operating systems work. So going further into the types of parallelism, we have the data parallelism and the task parallelism. And for the data parallelism, it distributes subsets of the same data across the multi-cores. So you have the data broken down into different sets, and then divided into the different cores. We're going to see a diagram shortly to kind of internalize that. And then for the task parallelism, here the threads are distributed across cores, and each thread performs a unique operation. So here is the difference. In the task parallelism, you can have different operations being run by different threads, but in the data, you're actually distributing different subsets of the same data across multiple cores, and the operation is on each. So if we are to look at the diagram here, you see we have data parallelism here. Subsets of the data are sent to different cores, okay? And then here for the task parallelism, each thread is sent to different threads are sent to the different cores, and then finally brought back to the data, and then the output is sent out. So that's really the difference. Same process, different threads sent out, but this could be, yeah, different data sets and managing different process. Then that brings us to the user threads and kernel threads. And here we are looking at, okay, the kernel threads generally are those supported by the kernel, and then the user threads are the ones managed by the user level threads library. So when you declare a library starting your program, those are the user threads. You declare what libraries you want to use in your program, and so those ones you set. But for the kernel, it has its own threads that are set by the operating system manufacturers. So we have three primary thread libraries, and that is the POSIX threads, which are or PThreads, because P stands for POSIX. And then we have the Windows threads, and POSIX generally is really about the Linux kind of based systems, Linux, Unix, and Mac OS. And then we have the Windows threads, and then the Java threads. And then examples here for all general purpose operating systems include Windows, Linux, Mac OS, iOS, and Android. So remember, these two, of course, are for mobile, iOS and Android, but they have similar operations. They work more or less the same. The only challenge with iOS and Android is their resource constraint, but they all have like the same way of working. And I think that explains why you can have a mobile app also running on a machine. Then we come on to the okay, there's someone asking here, is it right to say that concurrency is like sequential execution and parallelism is simultaneous execution? Anyone with a view on this? Is concurrency like sequential execution and then parallelism simultaneous?
Yes.
Is there someone who wants to respond? Okay, depending on what you mean.
Excuse me.
Yes. Go on.
Could you repeat the question again?
Oh, it's in chat. Someone wrote and said, is it right if I say that concurrency is like sequential execution and parallelism is simultaneous execution?
Yeah, I think so. Because when you say parallelism, it is simultaneous. Like there are many processes maybe happening at the same time. Then the other sequential one, one is happening after the other. So I think it's correct to say that.
Okay. So Terry also agrees with you. and yeah, many others, Nabukera. So AMPA, yes, we could say that, yeah, I'm glad you're able to, get to just simplify it in that way. So yeah, concurrency, someone says, is in fact sequential, but jumping between tasks happens so fast that it looks like simultaneous execution. So yes, so thank you for that, and also for your contributions. Next, let's look at the multi-threading models, and we have generally three: many-to-one, one-to-one, and many-to-many. Now in the many-to-one, we have many user level threads that are mapped onto a single kernel thread, just like you see in the diagram. And so one thread blocking causes all to block. So if one thread gets blocked, then the others of course won't go through, because they are all leading to a single kernel thread. So that means if one is blocked, then the others can't go through to be processed in the kernel. Remember, this is a user space, this is a kernel space. And so multiple threads may not run in parallel on multi-core systems, because only one may be in a kernel at a time. So multiple threads normally will not run in parallel on a multi-core system, because we have a single one that will be running in the kernel. So it will, all of them will come here, but it's more or less one at a time that will be processed, then brought out, and so on. And there are a few systems that are currently running this model. And there is the Solaris. I think some of you have heard of the Solaris OS, and then the GNU. GNU, I think, is open source as well. And then the one-to-one, we have each user thread mapping onto a single kernel thread, just like we see over here. And so you create a user thread which creates a kernel thread. So once a thread is generated by the user, a subsequent or a kernel thread that will deal with that user thread also is created in the kernel. And this one really works on the number of threads per process sometimes, and might be restricted due to overhead. So of course, when the kernel can no longer handle, then some of the threads by the user will be kind of limited. And the examples of this is Windows. Windows works like that, and Linux. And then the many-to-many model, we have many threads by the user and many kernel threads. So maybe if there are 4 over here, yeah, 3 of them can be run through, these different 3 threads running, they are handled. And then of course, if others are generated and they are free kernel threads, yes, they receive them and work on them and send. So here we have many user threads to be mapped onto many kernel threads, and it allows for the OS to create sufficient number of kernel threads. And here, in this kind of scenario, Windows has the thread fiber package that helps to work on this kind of model. Otherwise, it's not very, very common. And then we have the 2-level model, which is similar to the many-to-many, only that it allows a user thread to be bound to a particular kernel thread. So the 2-level, you have a particular thread bound, a user thread bound to a kernel thread, just like the one-on-one. So, but you have so many of them, but each is bound to a particular kernel thread. Yes, someone is asking, is blocking the same as waiting? And yes, we could take it like that, especially if we are dealing with the operating system. So literally when a process is blocked, what is happening is it's kind of stopped. It's more or less in like the waiting state. And if you remember, wait is more like a system call. So it's wait and have brackets, and there is something that you have to input in that. So once it gets blocked, it's kind of in the waiting state. It has to, maybe it's waiting for an input or an output, and then it will continue. So that said, after looking at the different multi-level models, we'll look at the thread libraries. And these ones provide the programmer with API for creating and managing threads. And just like I said, normally when you're beginning to write your code, you write the libraries that you're going to use based on your need. And we have two primary ways of implementing. So the library is entirely in the user space, or there's the kernel level library, which is supported by the operating system. So sometimes the kernel will do it for you because it's set and supported by the OS, and then there's that within the user space where you select and use what you have to use. Then we have the PThreads or the POSIX threads, and these ones are provided either as user level or kernel level. And there's a standard API for the POSIX standard for thread creation and synchronization, of course, as given in the IEE regulations 1003.1c. So yeah, if you're curious or you just want to know more about it, you can read about that standard, IEEE 1003.1c. And then the specification, it's just a specification but not an implementation. And this API, the PThreads, specifies behavior of the thread library, and so the implementation is up to the development of the library. And it's common in Unix operating systems, that is Linux and the Mac OS. And then we have the implicit threading, or something that is like implied or suggested threading. This is actually generally done by operating systems, just to bring about efficiency. And this one is growing in popularity as numbers of threads increase, and program correctness becomes difficult, especially with explicit threads. So it's really about creating and managing of threads, and it's done through the compilers and the runtime libraries rather than the programmers. So it's some kind of working or ability of the operating system to kind of help in the program correctness and so on. And there are 5 methods that are explored under the implicit threading. There's the thread pools, the fork join, the openmp, grand central dispatch, and then there's the intel threading building blocks. So this is just so we understand, but we'll not go into detail of those 5 methods. Then there is the signal handling, and for the signal handling, this one is used in Unix systems to notify a process that a particular event has occurred, just like we did mention earlier when we looked at system calls. So this signal handling is similar to a system call, and the signal handler is used to process signals in 3 ways. There's a signal that is generated by a particular event, and then a signal that is delivered to a process, and then a signal that is handled by 1 or 2 signal handlers. And normally those signals handlers have values, one that is default and the other that is user defined. But every signal has a default handler that the kernel runs when handling a signal. So for the user defined signal handler, it can be actually overridden by the default, okay? And then for a single threaded, the signal is delivered to the process. Because remember, in single threaded, we said that you have more or less a single process with a single thread. So here, in a single threaded arrangement. You have the signal delivered to the process. And so the question arises, where should the signal be delivered for, or in the case of multiple threads or multiple threading? So the signal could be delivered to the thread to which the signal applies, or it could be delivered to every thread in the process, or it could be sent or delivered to certain threads in the process, and then it could also be assigned a specific thread to receive all signals for the process. So you could have a specific thread receiving all the signals for the process, or a thread, the signal is sent to a thread to which the signal applies, or the signal is sent to every thread in the process, and then the signal might be sent to a certain thread in the process. So those are the different scenarios in which the signal could be delivered, especially in the multi-threaded arrangement, because also for the single-threaded, it will be sent to a single to the process generally, because the thread is the process. Okay, and then we have the thread cancellation. We have the thread cancellation, and then the thread cancellation, here we're talking about terminating a thread before it has finished. And then sometimes the thread can be cancelled. The thread to be cancelled might be the target thread. And there are two general approaches when it comes to thread cancellation. There's the asynchronous cancellation, which terminates the target head immediately. And then there's the deferred cancellation, which allows the target thread to periodically check if it should be cancelled. So of course, just like we said, that some of these threads are subtasks within an entire process. We're saying that the cancellation of threads will depend. It's more like a parent and a child. So if you have to do certain tasks within the entire process, okay, if it's a batch system, there are certain things that have to happen for the whole system to work. Then if you realize that, okay, this task now is no longer useful, then that thread will be cancelled or terminated, and then the entire process will continue to go on. Sometimes the parent will end up, terminating, and obviously the child will terminate. So those are the deferred cancellations, which allows the target head to periodically check if it should be cancelled. So then when it realizes, okay, the process, maybe parent processes has stopped, then all the child processes will also be stopped. Then when you are invoking a thread cancellation, then a request has to be made for cancellation, but the actual cancellation depends on the thread state. So if the thread is running, then it might have to complete and then get terminated. Then if the thread has its cancellation disabled, then the cancellation remains pending until the thread is enabled. But the default type is deferred, just like we said. It keeps checking periodically to see if it can terminate it or not. And the cancellation will normally occur when the thread reaches the cancellation point. And there's that command pthread test cancel that can be invoked. Now for Linux systems, the thread cancellation is handled through signals, and we just looked at the signal handling and how it's done. Yeah. Okay. Yeah, so some people are giving answers in the chat, and that is a good one. Yeah, then lastly, we're going to look at the thread local storage. And the thread local storage allows each thread to have its own copy of data. And so you realize that each thread will have its own copy of data in the thread local storage. And this is useful when you do not have control over the thread creation process, especially when you're using the thread pool. So you have a situation where you'll have different local variables. It's different because you have different local variables. And then the local variables are also visible only during the single function invocation. Now this thread local storage is visible across function invocations. So you know the functions in some of the programming codes. So when you invoke a function, okay, then you will see some of these. Okay, the operating system will see some of the thread local storages, and then it will work accordingly. And it's similar to static data, but the TLS is unique to each thread. Just like we said, it allows each thread to have its own copy of data. So each thread will run separately, as opposed to what we looked at, if you remember, in the IPC, where we had shared memory and the inter-process communication, where we had also the messaging message passing. So here we have the thread local storage, which actually has a copy of its own data, and so it is unique to each thread, and so each thread can be able to run without any complication. And so lastly, we have that example of the Linux threads. And in Linux, the threads are referred to as tasks rather than threads. And the thread creation is done through that system called clone. And clone allows a child task to share the address space of the parent task. And the parent task now is the process. And so we have those different flags control behavior, where we have the clone fs, and that's the file system information that is shared. And then we have the clone VM, which is the same memory space that is shared. Then we have the clone signal handlers are shared, and the clone files, a set of open files that is shared. So these are just really syntaxes that are used in the Linux threads generally, but by the operating system. So this should not be really something that you need to like cram. It's like you have to for some of the commands maybe in C or Java. So this is all we have for today. Just like I said, I'll probably go over an hour. For some of you who are saying we haven't had a break, said I'll just do an hour. And so that is it for today, unless there are any queries, rather any concerns or comments. I would like us to end here, and then we'll meet next week. Just to reiterate what I said yesterday, someone asked about the tests and everything, but I'll come up with a schedule which I'll share on Mwele, so you'll be able to know when we'll have the tests, and then the assignment, first assignment and everything, and yeah, how we shall progress thereafter. And just so you know, some of the topics we are going to handle in kind of discussion. So actually I request your class reps, at least I'm in touch with them. I'm going to ask them to send me your groups so that I assign different groups, different topics. You go research and then come and we discuss in class. But I'm going to put up a schedule for that, and then we'll see how we go forward from there. Yes. Yes, Kajimu. I can see you raising your hand. Kajimu? Did you raise your hand by mistake, Kajimu?
I'm saying that we would like you to help us give us the recordings via.
Kajimu, I didn't hear you. But I can see Brian. Brian is asking for the recordings. I share the links on Mwele, so if you get into Mwele, you'll see all those things. But you're able even to receive an email. If you're registered on Mwele for the course, you're able to receive an email and see that the links I share. Then Mugaga, John Roy, the textbooks. Please refer to the very first slides, introduction slides. I put up the
Excuse me, sir.
Yes.
So you showed 2 books. So I'm wondering which of the 2 you actually take your notes from. That's all I'm asking.
I just get the 2 and come up with stuff that I share here. So you just need to try and read more from those textbooks from what I share. So if you really read through the textbooks, it's close to what I give here. So for me, I just generalize and then come up with what I share over here. So those are the sources. Not that they are wrong, but they are right. Okay. So Edward, you're still saying, but we are not seeing the recordings there. Who has seen the recordings on Mwele? The link. I don't put the recordings, I put the link. Anyone? By show of hands? Yeah, I can see people have seen it. So,
Yeah,
Edward,
I have seen them.
You've seen them? Okay, so you cannot say they're not there. I share links, so you just go and click on that link and then you will get, if you want to download it, you download it. So I cannot keep putting them up there. Like I've been saying, resources are limited on Mwele. Everyone is loading their videos and everything. So if I can put a link that each of you could access and download, I think it's better to manage the limited resources. All right then, so let's meet next week and have a great week.
Excuse me, sir, about the groups.